Section 2.1, Logical Form and Logical Equivalence. So, as we have statements, we are going to have two parts. The premise, which is basically what we are given, and the conclusion, which is where we want to end up. So, for logic, we want to know, is the overall statement true? And if there's more than one part of the statement, which of those parts are actually true? And as we follow the logic, we will then be able to say if this part of the statement is true and this part of the statement is true, for example, is the overall statement going to then be true? So let's look at some statements. We're going to often use P, Q, and R just to represent generic statements. So you'll notice for this one, we've got an if and a then, but within the if, there's actually two parts, because you'll notice we've got if P or Q, then C. So that's going to be a little bit more of a complicated statement. Here's another example of an argument. So here, again, I've got an if with two parts with an or and a then. So even though this first one we saw in the previous example had words, and this one has mathematical statements, logically we would say they are essentially the same thing. That next statement, we would do the same thing. It's if, and then my then has two parts with an and in between. These three little dots in a triangle out front, that means therefore. And that is what we put in front of our conclusion. So let's look at some statements. So the main thing we want to know about a statement, which we also call a proposition, is that it is either true or false, but not both. So if you have anything with a variable, that is not a statement, because some x values it works, and some x values it does not work. And again, if there's two variables, as you can see here, again, that is not a statement, because sometimes it's true, and sometimes it's false. All right, let's look at compound statements. So here we're going to have one or more statements, and we're going to have symbols. Our first symbol is this little tilde that indicates not. Our little up caret indicates and the down caret, or V, indicates the word or. Do note you will sometimes see this little symbol instead of the tilde. It kind of depends who's typing it and what symbols are available on the keyboard. Just like in regular mathematics, we do have order of operations. Not is generally going to be done first, and then the and or, unless, of course, we have parentheses. So if we compare these, I've got this not here out in front, and there's no parentheses. We understand it to be on the P. That means if I want the P caret Q to all be not, I do need to have parentheses around it. Do note if we have ands and ors, as you can see in this statement where I've got my mouse, we do try to put parentheses to be very clear about which one we're going to do first. All right, so we're going to take these statements and try to write them using symbolic logic. So we're going to use H for it is hot and S for it is sunny. And my first statement, it is not hot, but it is sunny. Now, but is not actually a symbol that we have, so I am going to interpret that with the word and. So I am going to write this as it is not hot and it is sunny, so tilde H and then my up arrow S. And finally, it is neither hot nor sunny. And again, I am going to rewrite that as it is not hot and it is not sunny. So I'll have my not H, or my tilde H, my little up caret, and then tilde S. Again, these two statements are different logically. All right, let's try some with mathematics. So if we have x less than or equal to 3, and again here we're going to have P is 0 is less than x, Q for x is less than 3, and R for x is equal to 3. So here for A, I'm going to have Q or R, and again the or is that little down caret, the V, because it's less we'd have x less than 3 or x is equal to 3. As you might recall, if we have 0 less than x less than 3, that is actually an and. We do understand that to be 0 less than x and x less than 3. So I would write that as p up caret q. And you'll notice I always put the and and the or on the side, just in case you can't quite remember which caret is which. And then last, 0 less than x less than or equal to 3, I'd have p, the up caret for and you'll notice that q or r I do have in parentheses. Alright, let's talk about truth tables. When is something true and when is something not true? So, we're going to make something called a truth table. And generally, this left-hand side I am going to give you. If I have just the one statement, it's either true or false. Remember, statements can't be both, they're one or the other. So the truth table for my negation, or my not, is we're just going to change it. And you can see then it went false and then true. Let's look at the conjunction, and conjunction is how we also refer to the and. So again, remember the and is my little up arrow. Here we are looking at two statements together, so the only time we will get a true for and is if both p and q are true. It's this first option. As you can see, all of the others, my conclusion is going to be false. Alright, that was a conjunction. Let's look now at the disjunction. So disjunction is our or. And again, you can see the down caret or v, so this is my or. This one, the only time it's false is if they're both false. So for or, it is true if even one of them is true, and it's also true if they're both true. And we will want to be familiar with these truth tables. Because now we're going to put together more complicated things and see if we can use a truth table to determine if the overall statement is true or false. And this is a discussion of how we're going to do it. Basically, I'm going to do each operation at a time, remembering what those truth tables look like. Do note here they are talking about something called the XOR, or exclusive OR. Think of that as the OR you might see on a menu, so soup or salad. That means you don't get both of them, you get one or the other, and that is different from the OR that we've already talked about. So, I am going to scroll past the explanation and go straight to the truth table. Here is our results. Now, generally on tests and homework, you will be given these left columns. And what I'm going to do is I'm going to slowly build up the other columns I need to get to my results. So you'll notice I've got the P or Q here. I've got P and Q. And then I did the not of P and Q. And then last but not least, I put those two things together with the and. And again, for each step here, we have to remember what the truth table looks like for each step as we then get that final result. And as you can see here, my final result was false, true, true, false. So let's try another one. Now here we're going to have three statements. We've also got the R. Now again, I'm going to kind of scroll through the description of how that solution comes about. Again, I'm basically doing each part at a time. And here you can see our full truth table solution. Now again, this left-hand side you will be given. You will not have to set that up. And again, we know what we're trying to get to. So this here is my solution. So again, I do each of those pieces. So you'll notice I did the part for P and Q. And as I'm doing that, I'm really just looking at these first two columns. I then did not R, and then those two columns I put together with an OR. And as you can see, there are only three places here where my conclusion is false. All right, let's talk about logical equivalence. So this is where we have two logical statements, and we are saying that they give us the same results. Basically, their truth tables are the same. And the notation that we will see here, it looks a little bit like an equal sign. There are actually three lines there. Think of it as being pretty much the same as an equal sign. So to do a logical equivalence, we're basically going to do the left-hand side with a truth table, then we'll do the right-hand side with a truth table, and if they are equivalent, those two columns should be the same. If they are not, then we don't actually have an equivalence. So let's do an example. Here we've got the double negative. So not P is equivalent to P. And here is my truth table solution. Again, the left part I've given, which is P. So I did not P, and then not P. So here I'm looking at that first column and the last column, and I'm saying, yes, they are exactly the same. So that means these two things are indeed equivalent. Let's now look at two things and show that they aren't equivalent. So here I've got not, and then P and Q in parentheses, and then not P and not Q. So again, here I'm given that left side, and again, I'm going to have to make a couple things to help build my way up. But you can see here's the left side, here's the right side. Now some of those options are the same, but again, in order for things to be equivalent, every single thing here in both these columns have to be the same. And since that is not the case, we would say that they are not logically equivalent. And for what it's worth, we were just doing what's called De Morgan's law. Think of it as if you are distributing a not across an and or an or, it changes. So as you see here, if I had an and, it becomes an or, and if I have an or and distribute the negative, it turns into an and. And both of those De Morgan's laws are pretty significant. So let's take these statements and write a negative using De Morgan's law. So here I've got an and. If I make a negative, it's going to turn into an or. So I get is not 6 feet, or he weighs less than. We had at least here, so less than would be the opposite. The next one, similarly, I have an or, so when I do the negative, it's going to turn into an and. So the bus was not late, and Tom's watch was not slow. We can do the similar thing for an inequality, and again, that's a three-part, so I'm going to mentally write it with an and. So again, De Morgan's law, the negative, I change each of those signs, and generally we try not to write is not less than. I would change that to greater than or equal to, just for ease of reading. And we can also write that on the number line. The last thing I'd like to talk about in this section are tautologies and contradictions. A tautology is something where my result is always true for every single option. And a contradiction is something where I always get a false statement. So let's look at a tautology. So let's start with P or not P. So again, I've got P, and I'm going to make a couple things to get what I want. And if we look at P and then P or not P, I have all truths there, regardless of what happens. Here we do also have a contradiction in the form of P and not P, and you can see that here they are all falses. And these are our two classic examples of a tautology and then a contradiction. You'll also see we might write it symbolically with T for tautology, C for contradiction, and you can see that if we combine with a tautology, we get what we started with. If you combine with contradiction, though, we will get a contradiction. And we're going to write that out with a truth table as well. Again, you can see here we've got the same truth values there, and here we've got the same truth values here, which are all, of course, falses, because that's where my contradiction is. And here's just a quick summary of some of our equivalences. You do not need to have these memorized. You will see a lot of them in the homework. So our last example here, I've got this logical equivalence. And again, the way we could do it is with a truth table, or we could use those properties and work it out that way. And that is everything in section 2.1.